Hi, I'm Don from Don Drones On. The more you know about how your drone thinks and operates, the more likely you are to avoid problems and know how to deal with problems should they occur in flight. For this reason, Transport Canada expects drone pilots to understand an immense amount of detail about RPAS systems. I'm going to go through these systems using a typical quadcopter as an example, and I'll talk about unique fixed-wing RPA systems towards the end. Let's get into it. A quick review of terminology. In Canada, your drone, this lovely blimp of a beast in this diagram, you'll see why, is officially called an RPA, or remotely piloted aircraft. Sometimes you'll see a lowercase s in front of that to mean a small RPA. Your controller is called the GCS, or Ground Control Station, which communicates with the RPA via a Command and Control, or C2, radio link. The whole thing combined is called an RPAS, or Remotely Piloted Aircraft System. Now we'll walk through all the key subsystems that make this work. Ground Control Station, Command and Control Link, Drone Transceiver and Antenna, Flight Controller, Position Sensors, GPS, Compass, Altimeter, Inertial Measurement Unit and related sensors, Electronic Speed Controllers or ESCs, motors, propellers, batteries, the payload, and, as I said, the fixed-wing specific components. And to finish off, I'll talk about inspection and maintenance requirements. The GCS system typically consists of a phone with flight software on it, a control unit with joysticks and lots of other controls, and antennae to communicate with the drone. To operate properly, it is imperative that all systems, the phone, the control unit, the drone, and even the batteries in some cases, are operating with compatible versions of software. So if your system calls for a software update, be sure that all these systems receive and properly accept the update. Don't ever fly with incompatible software versions. And I strongly recommend you only take updates from the manufacturer of your drone. Your GCS system communicates with the drone via a radio link, which may be a Wi-Fi link or something more sophisticated like DJI's OcuSync. Regardless of the sophistication, it is crucial to maintain what is called the radio line of sight. Radio line of sight is very similar to visual line of sight, with one weird difference. Radio signals can be partially degraded by direct obstacles, of course, but they can also sustain interference from obstacles near the radio path due to something called the Fresnel zone. Radio signals degrade with distance, interference from buildings, hills, water, and vegetation, and also interference from other radio sources like Wi-Fi signals, cell phone towers, electromagnetic noise from power lines and transformers, all sorts of things. The OcuSync system I mentioned actually monitors radio signal quality and actively switches channels to optimize the connection. That's why it works so well. If the C2 link is lost, and it happens to everyone eventually, attempt to regain connection by facing the drone, reorienting the antenna on the controller, remembering that the signal propagates out of the sides of the antenna, not the ends, and moving closer or moving somewhere to avoid obstacles. In the worst case, restart your controller. Many drones have an RTH, or Return to Home Autonomous mode, which kicks in if your C2 link is lost for a period of time. If your drone is equipped with that feature, ensure that it is enabled as part of your pre-flight check. This is the kind of setting that can be messed up by software updates. Also ensure that the return to home altitude is appropriate to clear trees or buildings or whatever in the flight area. Now, if you're moving during your flight, perhaps you've launched from a boat, for example, consider carefully other lost link actions, since an RTH may result in your drone happily landing in the water. Okay, back to the C2 link. On the drone itself, there is a corresponding transceiver and antenna subsystem, which receives the commands from the GCS and transmits back position, camera feed, and telemetry information like battery life remaining. The transceiver is tied directly to the flight controller, or the brain of the drone. The main purpose of the flight controller is to drive signals to the motors to implement the pilot's movement requests, all the while compensating for whatever environmental craziness is going on, such as the wind. The flight controller also is performing obstacle avoidance based on whatever sensors your particular drone has. It must monitor battery conditions and report to the pilot the time remaining. It's also managing camera and gimbal positioning along with the image feed to the pilot. Now, depending upon the architecture of your drone, these functions could be all in one chip or distributed across various subcontrollers on board. In order to be able to execute the pilot's commands, the flight controller needs to know precisely where the drone is, how it is oriented, and the current velocity. This information is provided by a combination of the GPS, the IMU, and a slew of other sensors, which we will now talk about. By the way, on my diagram, I'm showing each item as a separate box. But like I said, these functions are often combined into a single module. The GPS and compass, for example, are often in the same module. Speaking of GPS, let's start by talking about that. The GPS, or Global Positioning System, is actually one of several global navigation satellite systems in operation. The other main ones being GLONASS and Galileo. A GNSS system derives the drone's latitude and longitude based on signal timings from orbiting satellites. Generally speaking, the more sky your drone can see, the more satellites it will lock onto, and the more accurate the positioning. In urban areas with many tall buildings and in mountain valleys, you will see fewer satellites, for example. Also, during strong geomagnetic storms, the time signals from the satellites can be distorted, resulting in inaccuracies. Let's look at a couple of other crucial sensors. First is the magnetometer, or simply put, the compass. This device electronically detects the Earth's magnetic field to determine the direction to magnetic north. Magnetic north, of course, is not the same as true north, and the variation between the two directions, called the magnetic declination, differs from location to location. For example, Toronto's declination is about -10 degrees, but the declination in Montreal, only 500 kilometers away, is -14 degrees. It is this variation that explains why your drone will want you to recalibrate its compass if you change locations. Yeah, the dreaded DJI dance. Also note that your compass accuracy can be impacted by power lines or the frame of your car and lots of other things. Here's another key sensor, the altimeter. The drone's altimeter detects the barometric air pressure and can determine the difference in height between a flight location and the launch site based upon the difference in air pressure. The combination of GPS, compass, and altimeter provide the drone with a fairly precise determination of its location in space and its orientation. But it depends upon one more device for that rock-steady hovering that we've become so used to. And this comes down to the IMU, or Inertial Measurement Unit. Ultimately, it is the IMU that is responsible for telling the flight controller the finer details of how the drone is moving in three-dimensional space, how fast it is moving, and in what direction. The sensors it uses for this incredible task depends upon the model of your IMU, but typically it uses multiple microscopic accelerometers and gyroscopes to detect tiny changes in location, altitude, yaw, pitch, and roll. And it sends all this data hundreds of times per second to the flight controller. The flight controller uses the information from the IMU in combination with the GPS, compass, and altimeter to put together the complete picture of the drone's location and motion. The only issue here really is that the IMU is so dependent upon these very sensitive sensors. If they're off even a little bit, measurements can start to drift and the IMU can essentially become disoriented. For this reason, it is critical to recalibrate the IMU when the system suggests it and to do a recalibration periodically, even if your drone doesn't ask you to. Don't do it before every flight, but perhaps once a year, or if you see your drone acting a little strange, like drifting or not keeping a perfect horizon line. These are telltale signs that your IMU needs calibration. Okay, so based on all of this information, the flight controller determines which propellers need to do what and provides appropriate instructions to those electronic speed controllers, or ESCs. There's one ESC per motor. The ESC's job is to deliver exactly the right current and voltage from the battery to the motor such that it rotates at the correct RPM. Let's talk about drone motors for a minute. The electric motors on a drone are quite different than a motor on, say, a desk fan. A regular electric motor has brushes that pass electricity to a rotating armature surrounded by fixed magnets. Drone motors, on the other hand, are brushless and are usually an outrunner design. In an outrunner design, the outer part of the motor rotates, and it is the inner stator unit that is fixed. And since the stator isn't rotating, it doesn't need those nasty friction-generating brushes. Hence, brushless. Although brushless motors tend to be more expensive, they're way more efficient and better performing than brushed motors. They also tend to be quite exposed, so be sure to keep dirt and grime out of them and especially keep moisture out. Don't fly your drone in the rain or snow. Propellers. In the standard brushless outrunner motor design, the propellers are attached to the outer part of the motor, the part that spins. Perhaps that's too obvious. The propellers are counter-rotating, 2 clockwise and 2 counterclockwise to cancel out the torque. And a pattern of RPMs across the various props will determine the kind of maneuver performed by the drone. I explain this more fully in my Theory of Flight Part 3 video, so I won't repeat myself here. Before and after every flight, carefully examine your propellers for chips, cracks, or deformation. These little guys are probably the cheapest replaceable part on your drone and what ultimately keeps it in the air. Replace damaged or worn propellers immediately. Just be sure to match the required direction of rotation. I mentioned that the ESC delivers power from the battery to the motors, so we better talk about the battery now. Drone batteries are usually lithium polymer or LiPo batteries, although some drones, like the original DJI Mavic Mini, use lithium-ion batteries. LiPo batteries, at least at the present time, provide the best energy-to-weight performance and offer a very high discharge rate. In technical terms, they have a lot of oomph and they can deliver it fast. LiPo batteries usually are configured in packs with 2 or more individual cells hooked up in series. When you look at the specs for your batteries, you'll see terms like 2S or 4S, which indicate how many cells are connected. Each cell provides about 3.7 volts nominally, but a full charge is typically 4.2 volts. Like the saying goes, with great power comes great responsibility. LiPo batteries can be a bit finicky and need to be carefully handled. While they can be charged and recharged many times over the course of their life, if they are discharged or used under load below about 20% of their capacity, then they can be irreversibly damaged. The minimum safe recharge voltage is 3 volts per cell. Similarly, overcharging a LiPo battery can damage the battery and could even catch fire or explode. Now here's where it gets tricky. Since over-discharging or overcharging can occur for a single cell within a multi-cell battery, It is important to frequently check the balance of your individual battery cells within a pack. The DJI apps include this capability. Oh, and never attempt to charge a frozen or very cold battery. Let it come up to room temperature before putting it on the charger. Between flights, it is best to store your batteries at about 50% discharged if you don't intend to fly for a few days. Storing your batteries fully charged will result in reduced capacity over time. Carefully inspect your battery before each and every flight and before each and every charge cycle. Any swelling, cracking, oozing, or weird smells coming out of the battery mean the battery is damaged and dangerous. Check with your local municipality for how to safely get rid of it. If you do have the misfortune of having a LiPo battery fire, attempt to smother it with a heavy inert substance like sand or dirt. A regular all-purpose fire extinguisher may prevent the fire from spreading, but it will not extinguish the battery itself. Never attempt to extinguish a LiPo fire with water. Surprisingly, you are permitted to travel on aircraft with LiPo batteries. In your carry-on luggage, though, not in your checked luggage. Individual batteries must be less than 100 watt-hours. For reference, a Mavic 2 battery is 59 watt-hours, but a Matrice 200's battery clocks in at 175 watt-hours, over that limit. I would advise checking with your airline in advance to ensure you won't run into difficulty at boarding time. The last item on our strange drone diagram is the camera, or more generically, the payload. The payload is defined as anything that is attached to your drone that is not required for flight. So any cameras, other than cameras used for obstacle avoidance, thermal sensors, laser mapping devices like LiDAR, agricultural sprayers or cargo would be considered payload. The weight of any payload at takeoff time is included when determining the kind of flight, for example, above or below the 250 gram threshold. So far, I've been focusing on quadcopter related bits and pieces, and many of these same components are used in fixed wing RPAs as well. Fixed wing RPAs do have a few unique elements, which we'll now cover. Because a fixed wing aircraft usually requires more area for takeoff and landing compared to a quadcopter, a defined safety area is required. It is a best practice to have what is called a safety template, that is a standard way to define danger zones during takeoff and landing. Fixed wing RPAs often need a boost of speed at launch time to reach flight velocity. This can be as simple as a strong toss in the air or as complicated as a catapult. Catapults can be powered with special bungee cords, springs, or even pressurized gas. Once in the air, fixed-wing RPAs need a mechanism to manipulate the control surfaces, such as the rudder, ailerons, and elevators. These are typically controlled remotely using a device called a servo. Since servos are electromechanical, each should be carefully exercised before every flight to ensure they haven't failed or are about to fail, such as making weird, unusual noises. While in flight, fixed-wing RPAs sometimes use a pitot tube mechanism to measure airspeed, which of course is crucial for ensuring the relative airspeed over the wings is sufficient. Pitot tubes compare the dynamic air pressure forced into the end of the pitot tube to the static air pressure to measure the airspeed. This airspeed is called the indicated airspeed. When it is corrected for temperature and pressure, it is called the true airspeed and is the speed relative to the air mass that the aircraft is moving through. Always ensure pitot tube openings are clear of debris. How you land a fixed-wing RPA will depend upon the model, but can involve landing gear or skids on a runway, a net capture mechanism, or even a forced stall at a low safe altitude. Let's round this all off by discussing inspection and maintenance of all of these systems. Before and after every flight, you should inspect the critical elements of your RPAS, including at least the propellers, battery, hull, arms, and flight surfaces for cracks or other forms of damage. While it is usually not possible to physically inspect the electronics, absolutely address any warnings or messages that may come up on the display during startup, such as compass calibration. Also, if you receive a message, like an email, from the manufacturer of your drone of a mandatory action, carry that out as soon as possible. Keep records of your maintenance activities, particularly any such mandatory actions, firmware upgrades, and component repairs or replacements. Some drones have redundant or backup systems on board. For example, Mavic 2s have redundant IMUs. If your system tells you that the main unit has failed and the redundant unit is being used, don't just carry on. Repair the failed part as soon as possible. Otherwise, it's like driving around on your spare tire. Not a good idea. Well, there we have it. How the various systems and components of your drone, and even fixed-wing RPA, work together to create an amazing flying machine. I hope you have found this video informative and helpful. If so, please give me a thumbs up and drop me a comment down below. If you haven't already done so, please subscribe to my channel and ring that bell for notification of future videos. Thanks for watching.